Hello there. PIDF and control systems in general are one of the most important things that you need to understand to make an effective and useful robot. But from my experience, the resources on the internet for understanding PIDF and implementing it in your code are not that great. There might be some really great resources out there, but I personally haven't found them. So my goal today is to explain how PIDF works, explain how you can use it in your code, and hopefully waste your time as little as possible. Most of this will require basically no prerequisite knowledge except for a little bit of understanding of math, so just kind of algebraic manipulation, and a little bit of understanding of code. So I'm going to go over some code at points, but they're going to be relatively small sections. There is going to be a part that will require some understanding of calculus, but that's a small part of this, and you should get an idea for the entire thing without that understanding of calculus. And if you don't understand it, you can't just trust the formulas that I give and move on with your day. All right, let's get started. So first, what is PIDF? Well, it's an acronym. The P stands for proportional, the I for integral, the D for derivative, and the F for feed forward. That's cool, but what does it actually do? Well, it uses a sensor or sensors to perform an action. So for example, here I have a picture of a robot, and this robot is going to try to follow this black line around in a circle. It's going to use a sensor on the bottom of it, which senses how much of the black line it's on top of. And if it sees, oh, I'm not on top of very much of the black line, it'll turn so it stays on it. And if it sees I'm on the left of the line, it'll turn to the right, etc., etc. So when should you use PIDF? Well, anytime your robot needs to do something, automatically, it needs to do it carefully, it needs to do exactly. So some examples of this are driving a specific distance, moving an arm, rotating some specific number of degrees, aligning with a vision target, and there's lots of other examples. For our purposes, we're going to basically entirely be focusing on driving a particular distance, or at the very end, driving a distance in a particular way, so curving or something. Okay, so let's get started on the actual algorithm. What does the F in PIDF actually do? Well, it gives an estimate of the output of your system. For all of our examples from now on, the output of our system is going to be a motor power, a value from 0 to 1, which we supply to the set power or something function, which tells our motor how fast it needs to go. Now, feed forward does not rely on any sensors, so this actually isn't using feedback from the outside world. But it's an important starting point, so we're going to understand this first. So the simplified formula here is that your motor power is equal to F, which is a constant, some number, which we'll show how to determine in a moment, times speed. Fantastic. You give some speed, it gives you an estimate of the motor power that you need to run at that speed. So let's do an example. We're going to drive forward 1 meter in 2 seconds. That's our goal. Okay, well, motor power roughly determines speed, and 1 meter in 2 seconds is 0.5 meters per second. So going back to our formula, we know that our motor power is going to need to be this constant F, which we're still going to figure out, we haven't figured out yet, times 0.5, the speed we want to go at. Okay, but what is the value of F? We have no idea at this point. Well, we can figure it out quite deterministically. We have this formula here. But if we were to just plug in the value of motor power that corresponds to a speed we measure, we could determine what F should be. Okay, so how do you do that? Well, it's a pretty simple process. Put your robot on the ground in a clear area where it has space to drive forward. Drive forward at full power. You don't have to drive forward at full power, but it's just the easiest way to do it. You could also drive forward at half power if you really wanted, or just some number that you know. Then measure the time to travel some distance, or measure the distance that it takes to travel during some amount of time, and record those numbers. Great. Now you've got these numbers going back. We're just going to pretend, for example, that we traveled 10 meters in 2 seconds. Now you plug those values into your formula, distance 10 meters times 2 seconds, and a motor power of 1, right? Full power. And then you do speed equals distance over time. So we're traveling at 5 meters per second. Going back to our formula, plugging these values in, we find that F is equal to 0.2. Fantastic. This means that the ratio between the speed we want to go at and the motor power we need to roughly achieve that speed is 1/5 or 0.2. So how would you actually use this in code? It's not too bad. You have a final double here because it's a constant that you're never going to change. And to get the motor power, you simply supply the speed that you want and you return F times that speed. Fantastic. Super easy. So what will this actually do for us? How well is this going to do? You might write a command that runs your motor for 2 seconds, right? 2 seconds at what speed and at what power? We said here that we're driving 1 meter in 2 seconds. So that means a speed of 0.5 times an F of 0.2 gives us we need to run the motor at 0.1 power, excuse me. And your robot will probably drive forward around 1 meter. It's definitely not going to be exact. Your mileage will vary, right? It's going to sometimes be lower, it's sometimes be higher. What are some factors that can cause this? Well, the motors are not perfect. They don't run at exactly the value you tell them. You might run over a bump in the ground. You might get to a slippery part where your wheel slips a little bit. You might have a variation in the voltage of your battery. Lots of things are going to affect this. This is why I said it's an estimate, right? We know that roughly 0.1 power is going to make us go at roughly 0.5 meters per second, but it's not exact. So what do we do about this? Well, this is when the P in PIDF comes in. So P stands for proportional, and it's the simplest of the P, I, and D. All three of those are going to incorporate a sensor, but P is the simplest way to incorporate that sensor. So what P is going to do is it's going to nudge our motor power depending on if our sensor determines we're going too slow or too fast. So we have this new factor that we add into our formula. Now our motor power is equal to F times speed plus P times error. We'll talk about how to determine P in a second again. What the heck is error though? Error is simply the difference between what your robot is supposed to be doing and what it is actually doing. So in our case, if you had a sensor that measured motor speed, your error would simply be your wanted speed minus your actual speed. Just to get a more intuitive sense of this, and we can plug that in the formula here. To get a more intuitive sense of this, let's go through some examples with various speeds and see what it's going to do to our formula. So as before, we're still trying to go at 0.5 meters per second, but now we've got this other term, actual speed, which is being incorporated in to nudge our motor power. So here, if our actual speed was measured to be 0.4 meters per second, we would plug this into the formula and find that our P is times 0.1. So whatever your P value is, it's going to end up increasing your motor power slightly. Just think through that and make sure that makes sense to you. If you have your speed too low, your motor power needs to go higher to compensate for that. Similarly, if your actual speed was measured to be 0.6, then the difference between your wanted speed and your actual speed would be negative 0.1, and then you want your motor power to be decreased because you're going too fast. Fantastic. How do you find P? Well, sadly, it is not by any means as easy as finding F. There actually isn't a way to deterministically find it. I'm not going to go through this in much detail, but you want to test your robot in some simple cases with various values of P. And to give you a head start on how to figure this out, here's some behaviors you will see if your P is wrong. One of the behaviors is called overcorrection. You'll see that if you tell your robot to drive at 0.5 meters per second, whenever it goes slightly over 0.5 meters per second, it'll overcorrect and go way too slow. And then it's going too slow, so it'll overcorrect and go way too fast. And you should see your robot kind of wiggling as it travels, oscillating wildly around the value you want it to. And there's also undercorrection. Undercorrection is when you set your p-value to be too low, and you'll notice this isn't really doing anything for me. Even though my sensor is telling me that I need to go faster, the robot isn't responding to that sensor's information. Your p-value is too small. Play around with p-values, you'll get a sense eventually for what it looks like. All right, and how would you use this in code? Also not too bad. We're going to have another constant p, which is equal to 0.1, and now our formula has been slightly changed. So not only do we need to know the speed we want to go at, we also need to know the speed that's been measured from our motor, right? And you're doing this every single tick. You're getting you're getting a new measured speed, and you're using that to update what your motor power should be. So we have our same F times speed term from before, but now we're also adding P times speed minus measure speed. Fantastic. Let's talk about I and D. Just a forewarning, these are less important than P and F, in my opinion. So, understand them, implement them if you'd like to, but I often find that the time it takes to tune these parameters can be better spent on other things. So what do they do? Well, I stands for integral and D stands for derivative, as we mentioned before, and they're harder to tune correctly and less important, as I said. So what is the formula after you put in these two terms? Well, you get two extra terms that you add, I times the sum of error and D times the difference of error. Okay. And what do these things mean? Well, sum of error is going to be the total sum of all the values the errors since you began the motion. And the difference of error is going to be just the difference between current error and the last error. So what do these things actually do? Well, I accounts for long run errors. So if you had a robot that wasn't driving fast enough, right? So you had a positive error for many ticks in a row, it's going to add up all of those errors, and it's going to keep pushing the robot harder and harder and harder as those errors accumulate. D accounts for sudden changes in error. So if your robot ran over a bump and the speed suddenly decreased, you would have this D term, which would give your robot a big nudge to quickly get back to the speed where it should be. How do you find these terms? How do you tune these constants? Well, it's very difficult. I don't even have advice on how to do this. I don't like tuning these terms. If you have low friction in your system, low static friction, if you have your F set correctly, and if you do a path blending, which we'll talk about later, you might not need I and D at all. So, with a grain of salt, maybe just set these to 0. So how do you code these in? It's not too hard at all. I set I to 0.001 and D to 0.01. My memory is a little hazy on this, but I remember it being roughly like a good starting point for I was 100th of P, and a good starting point for D was 1/10 of P. And you're going to need two variables now. You're going to need a total error, and you're going to need a last error. And so you can see in this function here, we accumulate that total error, we add the current error to it, and we take the difference between the current error and the last error, and then update last error so that the next time a tick happens, we'll still be taking the difference between the current and last error, and then you just add all the terms like before. This code is all very simple. It should be not a hard thing to understand if you have a little bit of experience with Java. All right, so what are the problems with this? Well, we said we wanted to go 1 meter, right? But really, we haven't tested that we go a meter. What we've done is we've gone for 0.5 meters per second, or as close as we can, for 2 seconds. This isn't great, right? Even if we have PID tuned exactly, or as well as we possibly can, there's going to be variations in our speed that we simply can't account for. So this isn't exactly what we want. What we really want is, since we want to travel 1 meter, we would like to use the distance traveled as the error, right? Because we want to say, if we've gone over 1 meter, we've gone too far. If we've gone under 1 meter, we haven't gone far enough. And then hopefully this will result in us going exactly 1 meter. That is the goal. Okay, what could we do? Well, if we did 1 meter minus the current distance, right? So the error would be 1 when you begin your path, and 0.5 when you're halfway through, and 0 when you've reached the end. This isn't great because you really want your error to be as small as possible. A large error means something has gone wrong. It's there in the name. Big error, bad. So this isn't exactly what we want. So what's a better way to do this? Well, path planning. This is definitely going to be the most difficult topic of this video. So strap in. This is when our wanted value, right? Before, our wanted value was our expected speed, but now it's going to be our expected position or distance. This is when our wanted value is going to change over time. So from now on, we will be using current distance traveled to calculate error instead of speed. This should be you should easily be able to get this from an encoder. So when the path begins, our expected distance traveled is simply 0 meters, right? We don't expect to have gone anywhere yet. So our expected distance is 0. When we're halfway through the path at 1 second, we should have expected to travel. We expect to have traveled 0.5 meters at this point. And similarly, when we're done, 2 seconds have passed, we would expect our distance is 1 meter. Okay, great. So what does this do for us? Well, you can make this nice graph here where you see on the x-axis we have time that's elapsed, and on the y-axis we have distance that we expect to have traveled. Okay, and as you can see, when it reaches 2 seconds, it levels out, stays at 2. Fantastic. Why is this better? Well, our expected distance now more closely matches reality, right? Before, if our expected distance was just 1 meter the whole time, we don't actually expect to be at 1 meter when the motion begins. So now we're matching reality more closely, and that's great because, firstly, we'll get closer to traveling 1 meter, and secondly, PID has to do less work. We're basically using the information we know about the real world, to make that error small. The more work your PID is doing, the more chance something goes wrong and you go off the path you're intending to go on. How will this affect our feed forward? The feed forward algorithm is depending on the speed that we want to go at. However, just like our distance changes over time, we also have a speed that changes over time, right? For the beginning of our path, starting at time 0, we expect to go at 0.5 meters per second. And the instant we hit 2, we're expecting to go at 0 meters per second. How do we implement this in code? Well, we're going to need some new constants. Those constants being wanted speed and wanted time. Now, for this section, we said we're traveling 1 meter, so that means 0.5 meters per second for 2 seconds. We'll talk later about determining these numbers and not hard coding them, but that's just how it's going to be for now. And we're going to need 2 new functions here. So these 2 functions are expected speed and expected distance. So we'll start with expected speed, which is the simpler one. This takes in the elapsed time, and it returns to you the speed you expect to be going at that given time. And this function, along with the expected distance function, is just meant to imitate the graphs that we showed before. So, for example, the expected speed graph here, if the elapsed time is less than the wanted time, if we're before or at 2 seconds, we're just returning the wanted speed, 0.5 meters per second. And once we've passed that time of 2 seconds, we're just returning 0, right? We don't want to be moving anymore because we should have completed the motion ideally. And then in this next function here called expected distance, we're taking in the elapsed time, like the other one, and we're trying to imitate that graph with the diagonal line and then plateauing at the top, just like before. So we have, if elapsed time is less than or equal to wanted time, same idea as before, return expected speed at the current time times the elapsed time. And this is pretty simple. I mean, this is just y equals mx plus b, where we don't even have a plus b because our y-intercept is 0. So we're just saying whatever the speed is, which is going to be 0.5, times the time is going to give us a line with slope 0.5, which is perfect. And then, this part's a little bit tricky, but not too bad. Otherwise, we're going to return the expected distance at the wanted time. And so this is a recursive call. So this might seem a little scary, but it's not that bad. Basically what we're saying is once the time has exceeded 2 seconds, the distance we want to be is the distance we were at when we reached 2 seconds. Basically what that's saying is the distance of this section of our function should be equal to where we ended in the previous section of our function, which makes a lot of sense, right? We go, our distance increases until we hit 2 seconds. And at that point, we're no longer dependent on the time. After 2 seconds, we should be staying at 1 meter the whole time after. Okay, and what does this change in our PID engine function? Well, firstly, instead of taking in a measured speed, we're taking in a measured distance. And instead of taking in a speed we want to travel at, we're making that a constant. What we really need to know is what is the expected distance at the current time. So for that reason, we need to pass into our function how much time has passed. And instead of our speed being some constant, our speed is just equal to the value that's returned by our expected speed function. And then after that, everything else in our PID function is exactly identical. Okay, so that was the easier bit of path planning to understand. That part you need to understand. Okay, this next part, it's important, but it is calculus. So, ask a friend, find a YouTube video, take calculus AB. You shouldn't need any, it's not high level calculus by any means. It's definitely intro calculus level stuff. So it's definitely understandable, but if you don't know calculus yet, this stuff could be very, very confusing and unfamiliar to you. But here are the key takeaways. The derivative of your distance over time graph gives you your speed over time. So for those of you who know what derivative means, you know it means slope. And we can see with a straight line, the derivative of a straight line is simply the slope of that line. So you can see this straight line here has a slope of 0.5, right? If we take its rise, which is 1, over its run, which is 2, we get 0.5. And then after 2 seconds have elapsed, we can see that the slope of our line becomes 0. And that's reflected in this graph here, where we can see that the speed is 0.5 and then it goes to 0. And similarly, the area under your speed over time graph gives you your total distance. Okay, so I should have actually just done this, my apologies. Let's take a look at these two graphs. So as I already talked about, the slope of the graph on the left is giving you the values of the graph on the right. And the inverse of that is that the area under the graph on the right is giving you the total distance traveled, represented by the graph on the left. So an easy way to determine this, looking at your speed graph, you can see we have a rectangle with a height of 0.5 and a length of 2. 0.5 times 2 is 1, and that's reflected how in our distance graph, when we're done, we've traveled 1 meter. Okay, so that's fine, but so far we haven't made our path any better. We're just doing some calculus stuff. What's the point? Well, velocity can't actually go from 0 to 0.5, right? Your robot can't do that. It takes time to accelerate. So we're not really matching reality. What do we want to do? We would like our velocity curve to tell our robot to go from 0 to 0.5 over some amount of time, right? We don't want to ask it to do it instantly because that's going to cause error. And like I said before, our goal is to reduce the error as much as possible. Okay, then we want it to hold at 0.5 and then go back from 0.5 to 0, again, over some amount of time. Because we can't brake instantly either. It takes some amount of time to slow down. So here is what's called a trapezoidal velocity curve. So you can see that our velocity here is going to start at 0, then it's going to linearly increase to some maximum value, some maximum speed. It's going to plateau at that maximum speed for a couple seconds, and then it's going to decelerate linearly to a speed of equal to 0, and it should reach that at time equals 2 seconds. And this is nice because we're going to be asking the robot to do something that's much more realistic, which means our error is going to be reduced. And this corresponds to this very, very nice looking position over time graph. You can see that the distance we've traveled slowly increases to some value. And then you can see we travel at a linear speed, right? Our speed doesn't change for some portion of this curve. Then it very nicely and gradually decreases to some value at time 1. So firstly, I know you can't click this link, but type it in. Maybe I'll put it in the description. This is a link to the Desmos graph that I'm using to generate these curves, which can be very helpful. So yeah, finding that trapezoid can be a little bit gnarly. It involves some calculus-y stuff. Just to give you a little idea of what's happening is we want the area under that trapezoid to be equal to the total distance we need to travel. And also the actual curve here is determined by taking the integral of this trapezoid. And it's also a piecewise function, which makes things difficult. So take a look at the Desmos. If not, just copy paste the code I have later, which I don't suggest, but if you need to, do it. Okay, so what is this trapezoid going to depend on? Well, 4 things. The total distance we want to travel, the total time we want to take to travel that distance, the maximum speed we want to go at, right? That speed we want to hold at. In our case, it was 0.5, and the acceleration we want over that period of time. So we know that the area under that trapezoid has to equal total distance. We also know that the trapezoid must end at a value of x equals total time. The height of the trapezoid should be equal to the maximum speed, and the slope of the sides are going to be equal to the acceleration. And all these factors are going to have interplay with each other. You almost always know your total distance in advance, right? These are one of these things that you can't change. So, your team tells you need to drive forward 1.5 meters so we can, throw a ball into a hoop. Okay, no changing that. And you should also probably set your acceleration in advance because it's kind of just determined by the physics of your robot. You can decide a good speed to go at. So this is one of these things you have control over. And then your total time is going to be dependent on all of those above factors. Time is one of those things that you don't know in advance how long you want your path to take. Okay, so looking at this, knowing this, let's now look at some code. All right, so first thing, I've changed up our constants a little bit. F, P, I, and D are all the same. We still have total error and last error, but we've got a whole bunch of extra constants here. We have total distance we want to travel. We have wanted speed that we want to max out at, and we have the acceleration we want to use to get to that speed. And then we've got some formulas here. So T3, this formula is one that is determined just by doing algebra, where you put the area of the trapezoid on the left side of an equal sign, you put the total distance you want to travel on the right side of the equal sign, and then you solve for total time. It's not a terribly difficult calculation. You can do it yourself, but also kind of boring. So I'm not going to talk about it here. Look at the Desmos, work it out on a piece of paper or a whiteboard, have fun. T1, again, wanted speed over Excel. This is just because looking back at the speed graph here, we can see that the time it takes to get from zero speed to our max speed here, which is like 0.8 or something, is just based on how fast we can accelerate. Then T2 is just the total time you want to take minus the time it takes to accelerate or decelerate. Okay, so this next section is going to be a little bit more confusing. So I am going to dedicate some time to this, more time than I did the previous section, to really explain this so that you understand, hopefully. All right, so what are these functions doing? For now, let's just look at expected speed. Expected speed is basically making what's called a piecewise continuous function. So piecewise continuous, the word piecewise here, if you don't know, means that it's a function composed of distinct functions within it, right? You can see we have, well, t is less than or equal to t1, we have one function, t is less than or equal to t2, we have a different one, etc., etc. And continuous means there are no gaps between the different piecewise functions. So an example of a piecewise discontinuous function would be this one right here. You can see that at t2, there is a jump, a discontinuity. A piecewise continuous function would be like this one. You can see that there are no discontinuities. This is clearly still a piecewise function, but it is continuous. Okay, and that is important because we want these functions to be continuous because it mirrors real life. Your velocity can't suddenly change in an instant. It has to take some time to change. Okay, so how do we actually implement this in code? Well, first let's take a look at the expected speed function here. Same kind of idea as the expected speed function before. We give it a time and it returns to us the speed we're supposed to go at that time. The difference is it's more complicated because we're trying to make it represent this trapezoid here. So just to quickly go over kind of the nitty-gritty details of making this trapezoid. Let's go line by line. So we start out here if t is less than or equal to t1. So if we're in the first section here from 0 to whatever t1 happens to be, we're simply returning acceleration times t, right? So that's pretty clear that that's going to create a straight line that looks like this. One interesting question that I should clarify here is why is the slope of this line equal to acceleration? And this is analogous to the way that the derivative of position was equal to speed. The derivative of speed is going to be equal to acceleration. In this case, because we have a straight line, the slope of this line is its derivative, and therefore that is its acceleration. So that's why we have accel here times t. Then in the next section here, this is the flat top part of the trapezoid, and that's just expected speed of t1. So that's where we left off in the previous section, right? And that's just constant the whole time because it's flat. And then we get to else if t is less than or equal to t3, and we have expected speed at the end of t2. So that's where we ended off right here, minus accel times t minus t2. So minus accel is because we're now decelerating down to 0. And t minus t2 is, there's a couple ways to think about this. The simplest way is just to say it's like point slope form, right? You want this negative acceleration line to have an origin point at t2 comma max speed, basically. And if you remember point slope form, that's how you do it in point slope form. And another good way to think about it is just to say this segment is beginning at time equal to t2. So in this segment, in the context of this segment, this right here is time 0, right? So to make this equal to time 0, we subtract t2 from it. A couple different ways to think about that. Play around with it, figure out what works for you. Just one last thing to mention is once you're past t3, then you're just returning 0 because you should have stopped completely, so you shouldn't be moving. And now we can take a look at what happens in expected distance. This one is definitely a bit more gnarly. So same idea, we give it a time, it returns us the distance that we expect to be at that time. So what's happening in this first bit here? Well, we're saying if t is less than or equal to t1, so if we're in this little curvy section of the position graph, then we're going to return 0.5 times accel times t. This might seem magical to you if you don't know calculus, but if you've done any calculus, this should be pretty familiar as the antiderivative of a straight line. So our straight line here is k times x, and the antiderivative is 1/2 kx squared. So in this case, accel and t instead of k and x, but same idea. And then in this next section, we're saying if t is less than or equal to t2. So this is going to be this straight line section of our position curve. Then first we're going to shift t back by t1. So this is the same idea that in the context of this section of the curve, this right here is effectively t0, right? And in order to do that, we have to shift it back. And we're going to return expected distance of t1, right? This is the distance we left off at in the previous section, plus the wanted speed times t. Right, so that's pretty clear. We're just saying the speed we're going at once we reach the top of our trapezoid right here. We're going to go along that line. Pretty clean. And then finally, if t is less than or equal to t3, so in this last section right here, the decelerating curve, we're going to again shift our t value back such that this position right here where the curve starts becomes t equals 0. and we're going to return expected distance t2. Same idea, we're starting out where we left off in the previous section, minus, again, same idea, we're taking the antiderivative of negative xl times t, so that's why it's negative half xl times t squared. That's where that negative sign comes from. And we're also, we have to take the antiderivative of both parts of this expression. So expected speed of t2, which is a constant, its antiderivative is that constant times t. And so that gives you this expression, and that will also end up giving you the equivalent of this curve. And then finally, when you've reached any time past t3, your curve should be done. And so your distance, no matter how far you've gone past that time, is just whatever distance you ended off at in the previous section, because you're not moving, so you should just stay there. Alrighty then. So let's bring it all together, as the title screen says. What we want to do now is, using all that we've learned, we're going to make a robot drive in a circle. So this is going to use the same techniques of having a trapezoidal speed curve and PID and all these different things. The main difference here is that in order to make the robot turn, the two wheels need to go at different speeds. So let's figure out exactly what that needs to look like. We're going to have a circle with radius 5 meters. And we're going to have an acceleration of 1 meter per second squared, a top speed of 1.5 meters per second, and we're going to go the full 360 degrees. We're not going to do a part of a turn. All right, so how do we make this circle happen? If you think about the path those two wheels would take, like in snow or in dirt, for example, you could imagine it would trace this path, with the inner wheel tracing the blue path and the outer wheel tracing the orange path. And the distance between those two wheels is the width of your robot. Sorry, the distance between those two circles is the width of your robot. Right? That should make a good amount of sense. So let's just do some simple math. What's the distance around each circle? The distance around the inner circle is 2 pi times radius, and the distance around the outer circle is 2 pi times radius plus width, right? That extra width from, that extra radius from the width of the robot. And we know that each wheel is going to complete their path around each of their circles at the same time, which indicates to us that one wheel must be moving slower than the other. Specifically, the inner wheel must be traveling slower than the outer wheel. Okay, totally fine. So let's pin this down a little bit. Our plan is going to be, we're going to find the speed and the distance curve for the inner wheel, and then simply multiply that by some ratio to determine what it should be for the outer wheel, such that we will travel in a circle. So what's that ratio? Well, the math isn't too hard. Speed is just distance over time. The times are the same, so outer speed divided by inner speed is just outer distance divided by inner distance. Those time variables cancel. And then plugging in the 2 pi r formula and the 2 pi radius plus width formula, math, you could do it easily. I just skipped a couple steps here. We have radius plus width over radius, and simplifying, we have 1 plus width over radius is our formula for the ratio between the inner speed and the outer speed. Great. So if we have a 5 meter radius and a 1 meter width, our ratio is going to be 1.2. Fantastic. So let's code this. The main difference in our code here is that each wheel needs a separate speed. Other than that, the code is pretty much identical. So not included here is this new variable called circle ratio, which is defined to 1.2, or can just be defined to 1 plus robot width divided by turn radius. That's also a great way to do it. And now we have two power functions. One of them is the power for the inner wheel. One of them is the power for the outer wheel. It's up to you if that's left and right wheel or right and left wheel. It just depends which way you want to go around your circle. The inner wheel power function is completely identical to the function we had before for power, right? No differences at all. And the outer wheel formula is actually nearly identical. The only difference here is that to find the outer distance, we take the expected distance, so the inner distance, we multiply that by the circle ratio. And to find the outer speed, take the inner speed, multiply by the circle ratio. Pretty clean and easy. And then we just substitute those values in, and that's going to give us the power we need for our outer wheel. And so, at this point, after writing all this code, you've got your path planning, you've got your P, I, and D, probably I and D are 0, and P is some value you've tested, and you want to travel in a circle. You should be absolutely good to go. You want to travel straight, just set their values to the same, set the powers to the same value for the left and right wheel. All right, so hopefully you have a pretty good understanding of PIDF now and how all this stuff kind of works. Some of the calculus stuff might be a little bit difficult, but other than that, I hope this all made sense. Before I head out, let's just talk very briefly about going further with this, because it is a very deep rabbit hole. So let's start with kind of something that might be obvious to you given what I've been talking about. What if we don't want to travel in a circle or in a straight line? What if we want to travel in an elliptical path or curves or curve left and right and do all sort of fancy things? There is a whole branch of probably computer science, I would imagine, dedicated to path planning. It can get very, very, very complicated, and have fun, delve into it, but also keep in mind that you may not need to have, the most incredible path planning algorithm to do exactly what your robot needs to do. There's also other ways of measuring error. So a great example of this is a vision target, like I mentioned at the very beginning of this. Very often you want to align your robot directly looking at a vision target. So that might mean that the vision target needs to be right in the center of the screen. So in that case, the error would be the difference between where the vision target is supposed to be on the screen and where it actually is. So maybe it's supposed to be in the center at pixel, 500 out of 1,000. So if it's at pixel 600, your error is 100 or something like that. That kind of thing can be really, really useful, and it's a pretty simple extension of what we've done here. You also can use multiple measurements of error at once. This is not something that I've explored personally, but you can combine these different measurements. Like if you had, a gyroscope on your robot and you had a vision sensor and you had encoders, perhaps you could put all these things together to get the most accurate possible reading of where your robot is on the field. And this is actually the most important one. It seems kind of silly, but this is really important. Make lots of nice graphs, because the easiest way to figure out where your PID is going wrong is by looking at graphs of what your robot is doing over time. So a really good one is to look at a graph of measured speed versus expected speed, and look at a graph of measured distance versus expected distance. Overlay those two graphs over each other. And this can give you a lot of information about how you need to tune your PID and what could be going wrong. More information, the better. And by far the most valuable thing you can do to diagnose errors is graph this information out. So I personally suggest using something like matplotlib from Python. Log your data, export it to a file, and then grab that file and put it on a computer and write a little Python program to convert that file into a matplotlib plot, and just take a look at what your robot's been doing. And yeah, I hope this is helpful. And if you have any questions, feel free to leave them in the comments, and good luck.